Alright, so welcome back to our third installment of waves, sound and light, and now we're into light waves. Although we cannot see how light travels, it displays the properties of transverse waves. Diffraction occurs when light passes the edge of an object, but it is not easy to detect. This suggests that light has a very small wavelength. When light falls on two narrow slits very close together, a pattern of equally spaced bright and dark bands called fringes is obtained on a screen. We can assume that diffraction occurs at each slit and that interference occurs in the region where the two diffracted beams cross. See these dark areas here? This is called destructive interference. All these dark areas are destructive interference. The bright areas are referred to as constructive interference. At points on the screen where a crest from one slit arrives at the same time as a crest from the other slit, waves are in phase and there are bright bands. Dark bands, however, where crests and troughs arrive simultaneously, that is where the waves are cancelled out. Okay, so a similar experiment was performed by Young in the year 1802. Nature of light. In the 17th century, there were two theories of light, the corpuscular theory and the wave theory. Both theories contradicted one another. The corpuscular theory regarded light as a stream of tiny particles or corpuscles traveling at very high speeds in straight lines. Newton supported this view. The wave theory considered light to travel in waves. This theory was proposed by the Dutchman Huygens. Opponents of the wave theory argued that waves needed to be carried by something such as water or air, but light did not appear to require one since it could travel in a vacuum. To meet this objection, the idea of a medium called the ether was invented, but despite many attempts, it defied detection. In 1850, the Frenchman Foucault showed via experiment that light traveled faster in air than in water, contrary to what Newton's corpuscular theory suggested. In the meantime, interference and diffraction effects had been discovered which were more readily explained in terms of waves than in terms of particles. Owing to this, the wave theory was developed further by the Scotsman Maxwell, who suggested that light was a transverse electromagnetic wave consisting of varying electric and magnetic fields traveling through space. Max Planck in 1900 put forward the quantum theory, which combined the wave and particle theories. In 1905, Einstein showed that the phenomenon of photoelectric emission cannot be explained by wave theory, but only by particle theory. On the other hand, particle theory could not explain phenomena such as diffraction and interference, which are clearly due to waves. Einstein had also shown that there is an equivalence between matter and energy in accordance with his famous equation, E equal to mc squared. Towards the end of the 19th century, discoveries were made concerning the emission and absorption of light by matter, which the wave theory could not explain. One of these was the photoelectric effect, in which light knocks electrons out of certain metals. Einstein explained this effect by suggesting that light was emitted and absorbed in small packets, quanta, of energy called photons. The quantum theory was then developed. Today, we accept both the wave and particle theories to explain the nature of light. They are now regarded as complementary and not contradictory. Light has both wave-like properties shown by interference and diffraction, and particle-like properties which justify treating it as rays traveling in straight lines, for example when considering reflection, as will be viewed later. Moving on into electromagnetic waves. Some general properties of electromagnetic waves. Electromagnetic waves are all transverse waves. They travel at the same speed, 3 times 10 to the 8 meters per second, through a vacuum or through air. They can propagate through a vacuum, and they consist of varying electric and magnetic fields. For all waves, electromagnetic waves can reflect, refract, diffract, exhibit the phenomenon of interference, and transfer energy. Diffraction is the spreading of a wave as it passes an edge or goes through a gap. Interference is a phenomenon which occurs at a point where two or more waves superpose each other, add to produce a combined vibration or amplitude lesser or greater than any of the individual waves. So remember that constructive interference is where two crests meet, and destructive is where you have a crest and a trough. Light is one member of the family of the electromagnetic waves. It is found in the visible region of the spectrum. So give some examples of electromagnetic waves. Correct. Gamma, X-rays, ultraviolet light, microwaves, radio waves, infrared rays. Right. So all electromagnetic waves exhibit reflection, refraction, interference, and diffraction, and travel at 300 million meters per second in air, which is the speed of light. Their different wavelengths and frequencies are related to their speed by frequency times wavelength. Okay, so all of them have the same speed, but the things that are different are their frequencies and their wavelength. Most of the electromagnetic waves result from electrons suffering some kind of energy change. An electromagnetic wave has both an electric field and a magnetic field, as demonstrated below. So here we have all the electromagnetic waves here, except in microwaves. I don't see microwaves. So the type is radio waves, radio transmitters, aerials that emit radio waves then when electric current oscillates within them. So that's the radio wave. Infrared is produced by all bodies above temperature 0 Kelvin or 0 Kelvin. Visible light produced by bodies above 1100 degrees Celsius. And you have RGB. Remember, visible light has all the 7 colors of the rainbow, which is red, orange, yellow, green, blue, indigo, and violet. Ultraviolet, very hot bodies such as the sun, 6,000 degrees Celsius, welding torches, electric sparks, and lightning. Gamma and X-rays are produced by, well, X-rays consist of high-speed electrons bombarding metal targets, and gamma rays are produced by changes in nuclei of unstable atoms. Now, microwaves and radio waves. Radio waves and microwaves are used for A, radio and television broadcasting, cell phone communication, and warming food, which is a microwave. Literally, a microwave produces microwaves to warm your food. Infrared radiation. So infrared radiation is detected by our nerves as heat. Anything which is hot but is not glowing, that is below 500 degrees Celsius, emits IR radiation alone. At about 500 degrees Celsius, a body becomes red hot and emits red light as well as IR. At about 1000 degrees Celsius, things such as lamp filaments are white hot and radiate IR and the white light. That is all the colors of the spectrum. Infrared radiation is used in ovens, toasters, and heat radiators, in remote controls, in fiber optic cables, in heat-seeking missiles, in treatment of muscular disorders, and by some animals that can detect IR from their prey in order to hunt them in the dark. Ultraviolet light or ultraviolet waves have shorter wavelength than light waves. It can cause suntans. What types of vitamins do they produce in the skin? Exactly, D. However, too much UV waves applied to the skin can be dangerous. Right? Too much of it can cause cancer, skin cancer. Now, UV radiation causes teeth, fingernails, fluorescent paints, and clothes washed in detergents to fluoresce. What does this mean? What does to fluoresce mean? Right, to glow. The shells of fresh eggs fluoresce with a reddish color. Those of bad eggs appear violet. A UV lamp used in science or medicine contains mercury vapor, which emits UV radiation when an electric current passes through it. Banknotes have a marking made of fluorescent substance, which becomes visible when UV is incident on them. This helps to discourage the circulation of fraudulent banknotes. Alright, so X-rays are produced when high-speed electrons are stopped by a metal target in an X-ray tube. Do X-rays have shorter wavelengths than UV rays? Well, to test this out, all you do is remember the saying reevux-gee. Okay, so reevux-gee, let's say reevux-gee, reevux-gee, with the M between the re. So this is radio waves, microwaves, infrared rays, violet rays, and then you have UV rays and X-rays. So remember, it's long wavelengths over here, and it starts getting smaller and smaller and smaller and smaller. So therefore, you would say that X-rays do have shorter wavelengths than the UV rays, right? Remember, a wavelength is like this. It's either between the crest and the trough, or between a crest and a crest and a trough and a trough. And to show you the other form, I'm going to put it here. That's one wavelength. This is another. So you could either go from this point to this point, or from this point to this point, or from this point to this point. That's how you measure wavelengths, right? Now, that's how you easily measure it. Alright, so X-rays to some extent are absorbed by living cells, but they can penetrate some solid objects and affect photographic film. X-rays do not pass through bones, teeth, and metals easily, and so shadow pictures can be taken. X-rays are used in medical imaging of dense materials such as bones or tumors within flesh, security scanning of passengers and luggage, and X-ray crystallography, a method of investigating the structure of crystals. Now, gamma rays are used to kill cancer cells. What else are they used to kill? Bacteria. Now, gamma rays are used in cancer therapy, imaging used in gamma cameras, and tracers. Are gamma rays more penetrating and dangerous than X-rays? You betcha. You betcha. They are. So that is why when cancer patients go for chemotherapy, a lot of times they come out sicker than they went in. The cancer cells might be dead, but also what is dead is the what is also dead, or what would have also died, are healthy cells. So gamma radiation is some serious stuff. Now let's check comprehension. Name 4 properties common to all electromagnetic waves. So we have reflection, refraction, diffraction, and they all travel at the same speed. Which of the following types of radiation has the highest frequency? So frequency means that the wavelength is shorter, and they bunch up together like that. It's closer, so more waves produced per second. And so the frequency, remember we said reevux-g with the m between the re, and the highest frequency will be at the end here. So what do we have? We have UV, we have radio, so radio gone, we have light, visible light, X-rays, so X-rays win. X-rays win. Name one type of electromagnetic radiation which causes suntan. Correct. Passes through a thin sheet of lead. Thin sheet of lead. Gamma. Gamma definitely is penetrating. Is used to take photographs in haze. Photographs. X-rays. X-rays. Okay. So a VHF radio station transmits on a frequency of 100 megahertz. So if the speed of radio waves is 3 times 10 to the 8, what is the wavelength of the waves? So we already have the frequency. So frequency equals to 1,000,000. How we can convert mega to hertz, and it gave the answer here 1,000,000 hertz. And we also have the speed, which is 3 times 10 to the 8 meters per second. And so if we have V equals to frequency times wavelength, and we're looking for wavelength, it will be V over frequency. So it's going to be 3 times 10 to the 8 meters per second over 10 to the 6 per second. We're going to be left with units of meters. 8 minus 6 is 2, so it's 3 times 10 to the 2. Right. Remember, when you have the same exponents here, you just subtract. So 3 times 10 to the 2. How long does the transmission take to travel 60 kilometers? So we have speed equals to distance over time. So t equals to distance over speed, and the distance is 60,000. Remember, the units for distance in SI is meters, so you need to convert to meters. Whenever you're doing calculations, convert to your SI units. So 60,000 meters, and then the distance, of course, is 3 times 10 to the 8 meters per second. And so you're going to end up with units of seconds. Because remember, m over s is equal to m over 1 times s over m. So that. And then we're going to have now, so this is, let's write it out. Let's see if we need to use a calculator. 10 to the 4 over 3 times 10 to the 8. And you're going to end up with 1 over 2 times 10 to the 4 seconds, which is actually 2 times 10 to the 4 seconds, which is actually 2 times 10 to the negative 4 seconds. If you calculate that, you should get that 6, 1, 2, 3, 4 divided by 3 times 10 to the 8, 2 times 10 to the negative 4. Yeah. So if you got that answer, good job.